a planet 30 times farther from our star than Earth, winds blasting at 1,300 miles per hour, storms bigger than our entire planet, appearing out of nowhere and vanishing just as fast, and somehow, deep inside, it is generating its own heat. Neptune is the most violent world in our solar system. We are going to travel through its screaming atmosphere, fall through diamond rain, watch a moon get slowly torn apart, and uncover the mystery that scientists still cannot explain. If you enjoy the journey, like and subscribe. It helps more than you know. Stay close. We begin. From 3 billion miles away, Neptune looks like a painting, a perfect, smooth sphere, deep ocean blue, calm, distant, almost peaceful. You could stare at it for hours and feel nothing but wonder. And that is exactly what makes it so dangerous. Every planet in our solar system has a personality. Mars is a dry, frozen desert. Venus burns under clouds of acid. Jupiter churns with storms the size of continents. But Neptune wears a mask. It shows you beauty. It hides the violence. And the violence on Neptune is unlike anything else we have ever found. Let's start with a number that is hard to picture. Neptune sits about 2.8 billion miles from Earth. If you got in a car and drove at highway speed without stopping, not for food, not for sleep, not for anything, it would take you more than 3,000 years to get there. 3,000 years. The Roman Empire had not even started yet. That is how far away Neptune is. And yet, even from that distance, scientists figured out something was deeply wrong with this planet. When astronomers first started studying Neptune carefully, they expected a frozen, quiet world. Makes sense. The farther you get from the star, the colder and calmer things should be. Mercury is hot and close. Pluto is cold and still. The rule seemed obvious. Neptune broke the rule completely. Telescopes picked up something strange in the atmosphere. Movement. Violent, fast, planet-wide movement. Cloud systems racing around the planet at speeds that made Earth's worst hurricanes look like a gentle breeze. Scientists checked their equipment. They ran the numbers again. The results kept coming back the same. Neptune's winds were faster than the speed of sound on Earth. That sentence alone should stop you cold. On Earth, if something moves faster than the speed of sound, you hear a sonic boom. Fighter jets break the sound barrier and shake windows miles away. Neptune's background wind, the everyday, normal, unremarkable wind that wraps around the entire planet, moves faster than that. Every single day. And nobody fully understood why. Here is what made it even stranger. Neptune receives almost no energy from its star. It sits so far out in the darkness that the light hitting its surface is about 900 times weaker than what hits Earth. You would need 900 Earths reflecting light just to match what we get from a single afternoon outside. Neptune gets almost nothing. So where is the energy coming from? That question would take scientists decades to start answering. And the answer, when it started taking shape, was even more unsettling than the mystery itself. The planet was heating itself. Deep inside Neptune, something was generating massive amounts of energy. Energy that had no business being there. Energy that was pouring into the atmosphere and powering storms on a scale we had never seen. The planet was putting out more than 2.5 times the heat it received from its star. It was running on something internal, something we still do not fully understand. Neptune was not just cold and violent. It was cold, violent, and alive in a way that defied everything scientists expected from a planet this far from the center of our solar system. You are looking at a world that should be frozen solid and silent, and it is screaming. The mask is beautiful. What it hides is something else entirely, and to understand it, we have to start at the most basic question of all. How does a planet this dark, this cold, this far from any warmth, produce the fastest winds in the solar system? Picture the solar system as a neighborhood. The inner planets are packed close together near the center: Mercury, Venus, Earth, Mars. They are all within a couple 100 million miles of the star at the center, warm, lit up, close enough to feel the heat. Then there is a gap. A big one. Jupiter and Saturn live in the middle distance, still getting reasonable amounts of light and warmth, still inside what you might call the neighborhood. Then come Uranus and Neptune, and these two are not in the neighborhood anymore. They are out past the edge of town, past the last streetlight, where the road ends and the dark just goes on forever. Neptune sits 30 times farther from our star than Earth does. 30 times. To understand what that actually means, try this. Hold up your thumb and imagine the distance from your thumb to the wall across the room represents Earth's distance from the star. Neptune would be 30 thumb lengths away, except instead of across the room, you are now outside, across the parking lot, past the street, halfway down the block. That is how alone Neptune is. Light travels at about 186,000 miles per second. It takes light about 8 minutes to travel from our star to Earth. You have probably heard that before, but it takes light more than 4 hours to reach Neptune. 4 hours of traveling at the fastest speed anything in the universe can move, and it arrives barely a whisper of what it started as. By the time that light hits Neptune's upper atmosphere, it carries almost no warmth. Temperatures up there drop to around negative 360 degrees Fahrenheit. That is colder than anything in your everyday life has any reference for. Liquid nitrogen, the stuff that freezes things instantly in science experiments, is warmer than Neptune's upper atmosphere. At that distance, at those temperatures, a planet should be doing one thing: sitting still. Neptune does the opposite. Scientists watching Neptune through telescopes in the 1980s started noticing cloud features moving across the planet's face. They tracked one cloud system and timed how fast it was moving. The answer came back and nobody believed it at first. The clouds were lapping the entire planet in about 16 hours. A planet much larger than Earth, circled completely in less than a day by clouds moving at supersonic speeds. This alone made Neptune one of the strangest objects in our solar system. Every other distant cold planet plays by the expected rules. Temperature drops, energy drops, activity slows. Neptune looked at those rules and ignored them completely. The farther scientists looked into it, the clearer it became that Neptune was drawing power from somewhere else entirely. Something inside the planet was awake, and that internal energy source was not a small quirk. It was the entire engine behind everything violent happening on Neptune. The winds, the storms, the chaos in the clouds, none of it made sense without first understanding that this planet had its own furnace buried deep inside it. But here is the part that really starts to shake your understanding of how planets work. The amount of extra heat Neptune produces is extraordinary. Scientists calculated it carefully. Neptune radiates more than 2.5 times the energy it receives from its star. Every second of every day, the planet pumps out more than twice the heat it takes in. That gap is enormous, and the source of that extra energy is one of the greatest unsolved puzzles in planetary science. Hold that thought, because to understand what that heat is doing, you first need to see just how fast Neptune's atmosphere is actually moving. Most people assume planets get their energy from their star. That is a reasonable assumption. Earth does. Mars does. Even Jupiter, giant as it is, follows that basic logic. Energy flows in from the star, warms the atmosphere, and drives the weather. Simple chain. Clear cause and effect. Neptune snapped that chain entirely. At Neptune's distance, the star's energy arrives so weak it can barely be measured against the planet's own output. Scientists have calculated this carefully. The amount of heat Neptune sends out into space is about 2.5 times greater than the heat it receives. Every single second, Neptune pours more energy into space than it ever takes in. That means something inside the planet is generating heat. A lot of it. Constantly. To picture this, Imagine a refrigerator that somehow makes the room it's sitting in warmer than the outside temperature. You are adding no heat source. The room should be cooler, but the refrigerator is putting out so much internal energy that it overrides everything around it. Neptune is that refrigerator, except it is a planet the size of about 57 Earths stacked together, and it has been doing this for 4.5 billion years. Where is that heat coming from? Scientists have two leading ideas. The first involves the planet's own history. When Neptune formed billions of years ago, enormous amounts of gas and rock crashed together under gravity. That collision released massive amounts of heat. Some planets radiate all that heat away quickly. Neptune, with its thick atmosphere and enormous bulk, may still be slowly releasing that original warmth, like a rock pulled from a campfire that stays hot hours after the flame goes out. The second idea involves something happening deep inside the planet right now. Heavier materials may be slowly sinking toward the core. As they fall, they compress, and compression generates heat. This process is still actively happening inside Neptune, releasing energy in a slow, continuous trickle that adds up to an enormous output over time. Neither idea fully explains the scale of what scientists are measuring. And that gap in our understanding matters, because that internal heat is the engine behind everything violent you are about to learn. Here is how it connects directly to the atmosphere above. Heat rises. Everyone knows this. Hold your hand above a candle and you feel it. The same basic physics works inside Neptune. As heat pushes up from the deep interior, it forces the atmosphere to move. The gas above heats up, expands, and rises. Cooler gas rushes in to take its place. That movement is what we call convection. And on Earth, convection drives weather. On Neptune, it drives something far more extreme. The convection currents inside Neptune are massive. The temperature difference between the deep interior and the upper atmosphere is enormous. That difference creates pressure. That pressure gets translated into movement, and that movement, on Neptune, reaches speeds that should not be physically possible in an atmosphere this cold and this dark. Scientists modeling Neptune's wind speeds kept getting results that seemed too extreme. They checked their work. The numbers were right. The planet's internal heat was pumping energy directly into the atmosphere at a rate that produced wind speeds beyond anything recorded anywhere else in the solar system. And you are about to find out exactly how fast that wind blows. Something in the data shocked every researcher who looked at it. They had expected fast winds. They had not expected what they found. Stand outside on a breezy day, and you feel maybe 10 or 15 miles per hour. A strong summer storm might push 60 or 70 miles per hour. Hurricane-force winds start around 74 miles per hour. The most powerful hurricanes ever recorded on Earth, the kind that flatten houses and push ocean water miles inland, top out somewhere around 200 miles per hour. Neptune's background wind speed is 1,300 miles per hour. That is the normal, the everyday, the unremarkable background circulation that wraps around the entire planet like a permanent belt of violence. 1,300 miles per hour, every second of every day, across a planet big enough to hold nearly 60 Earths inside it. For comparison, the speed of sound at sea level on Earth is about 760 miles per hour. Neptune's wind moves nearly twice as fast as that. If a fighter jet were flying through Neptune's atmosphere, the wind would be lapping it, the wind would be winning, and nobody saw it coming. When scientists first calculated how fast Neptune's atmosphere should move, they built their models on what they knew about other planets. Colder planets tend to have slower, more sluggish atmospheres. The cold thickens things, slows the molecular movement, dampens the energy. That was the expectation for Neptune. A cold, slow, nearly dead atmosphere sitting at the edge of the solar system. What they found instead forced them to rethink the physics. One of the leading ideas behind Neptune's extreme wind speeds involves friction, or rather, the lack of it. On Earth, when air moves across the surface, it encounters resistance. Mountains, oceans, uneven terrain all act like brakes. They slow the wind down, create turbulence, break up the flow. Neptune has none of that in its upper atmosphere. The gas just keeps moving with almost nothing to stop it. The extreme cold plays a role too, but in a backwards way from what you might expect. The cold removes a lot of the small-scale turbulence that normally disrupts wind flow. Instead of creating thousands of smaller competing currents that cancel each other out, Neptune's atmosphere allows large-scale flows to organize and build. The wind does not get broken up, it gets channeled. And once it gets channeled at Neptune's scale, it keeps accelerating. Picture a river. If the riverbed is smooth and straight, water flows fast. If it is rocky and winding, the water slows down and splashes everywhere. Neptune's atmosphere is the smoothest, most organized riverbed imaginable, and the internal heat engine keeps pouring energy into that river continuously. The result is the most powerful sustained wind in the entire solar system. These are not local gusts. These are planet-wide jet streams that circle Neptune completely, non-stop, at speeds that would strip away any structure, any landmark, any surface feature if Neptune had one to strip. The planet is encircled by a permanent ring of supersonic movement. But speed alone is only part of the story. What that wind does, what it builds and destroys in the atmosphere above, is where Neptune's true violence becomes visible. Because somewhere inside those screaming currents, something enormous was forming. A storm so large it could swallow the entire Earth whole. A storm that appeared suddenly, raged for years, and then did something no one expected. It vanished. In 1989, a spacecraft called Voyager 2 was doing something no human object had ever done before. It was flying past Neptune. Scientists on Earth had been tracking this mission for over a decade. Voyager 2 had already visited Jupiter, Saturn, and Uranus. Neptune was the final stop, and as the spacecraft curved around the planet and its cameras powered on, the images started coming back to Earth. 4 hours after leaving Neptune, the signal arrived. Scientists crowded around screens, and there, in the blue atmosphere, was something no one had expected to see so clearly. A dark oval sitting in the southern hemisphere of Neptune, perfectly defined, enormous. Scientists started measuring it against the planet's size. It was about 8,000 miles across. Earth is about 8,000 miles in diameter. The storm sitting in Neptune's atmosphere was the same size as our entire planet. You could drop Earth into that storm like a marble into a bowl. It would fit with room to spare. They named it the Great Dark Spot. To understand what caused it, picture the wind streams on Neptune. Those supersonic currents do not all move in the same direction at the same speed. Some flow east, some flow west. Layers at different altitudes move at different rates. When these layers grind against each other, they create massive rotational forces. The gas starts to spin, and on a planet with Neptune's energy output, once something starts spinning, it builds fast. The Great Dark Spot was a giant rotating storm system, similar in structure to a hurricane on Earth, but operating on a completely different scale. Winds around its edges were clocked at among the fastest on the planet. The storm pulled gas up from lower altitudes and flung it outward in spiral arms. It was organized, powerful, and visually striking. Following the Great Dark Spot around the planet was a bright, white cloud system that scientists nicknamed the Scooter. The Scooter moved faster than the storm itself, lapping it every few days. Scientists watched these two systems like a slow-motion race around an enormous blue track. From 8 billion miles away, Voyager 2 captured all of it in stunning detail during its flyby. And then the mission moved on. Voyager 2 had no way to slow down. It was on a one-way trip out of the solar system, so scientists turned to the Hubble Space Telescope to keep watching Neptune. 5 years after Voyager 2's flyby, scientists pointed Hubble at Neptune to get an updated look at the Great Dark Spot. They expected to see it still raging, A storm that big on a planet with that much internal energy should last for a long time. Jupiter's Great Red Spot had been raging for hundreds of years. The Great Dark Spot was gone, completely gone. The storm that could have swallowed Earth had vanished in less than 5 years. The southern hemisphere looked calm. New cloud features had formed in different locations. The slate had been wiped clean. Scientists stared at the data in disbelief. A storm, 8,000 miles across, had simply ceased to exist, and what replaced it made the mystery even deeper. The disappearance of the Great Dark Spot forced scientists to completely rethink how storms work on Neptune. On Earth, hurricanes form over warm ocean water. They build over days or weeks. They move across the ocean, weaken when they hit land or cold water, and die out. The whole process, from birth to death, might take a few weeks. The most extreme cases last a couple of months. Jupiter's Great Red Spot is on the other extreme. It has been spinning for at least 350 years, possibly much longer. Scientists are not entirely sure when it started. It is so stable, so persistent, that it has become one of the defining features of the planet itself. Neptune sits in a completely different category from both. After the Great Dark Spot vanished, scientists kept watching. And over the following years, Hubble caught something unexpected. New dark spots were forming on Neptune, fresh storm systems, popping up in different locations, and then disappearing again. These storms were appearing and dying on a timescale of years, possibly months. By planetary standards, that is almost instant. To understand why, you have to think about what makes a storm stable. Stability comes from balance. A storm keeps spinning when the forces pushing inward and outward are roughly matched. On Jupiter, the stable layers of the atmosphere lock the Great Red Spot in place like a groove in a record. The storm has a home. It stays there. Neptune's atmosphere offers no such stability. The internal heat engine is constantly churning the gas from below. The supersonic winds above are constantly shearing the atmosphere in different directions at different altitudes. There is no stable groove for a storm to settle into. Every storm on Neptune is fighting for its life from the moment it forms. Scientists have observed storm systems on Neptune that appeared, grew to the size of a continent, and then broke apart within a single year. From the outside, looking at the smooth blue atmosphere, you would never guess something that dramatic was happening. But underneath the visible cloud layer, the atmosphere is in constant violent upheaval. Here is the part that pulls at something deeper. Scientists began to wonder whether Neptune is continuously generating new storms as fast as it destroys old ones. If the internal heat never stops pumping energy into the atmosphere, and the wind never stops shearing the cloud layers apart, then the planet might be in a constant state of storm generation and storm death happening simultaneously. The atmosphere of Neptune could be a permanent battleground, storms rising and falling all the time, some growing large enough to see from Earth, most dying before they ever get that big. And then, during one of those periods of watching, Hubble spotted something unexpected. A storm appeared in Neptune's northern hemisphere, dark, clearly defined, growing. Scientists started tracking it. They braced for it to vanish the way the Great Dark Spot had. It did not vanish, at least not right away. What happened next gave scientists a rare and extraordinary window into the life cycle of a Neptune storm. And what they saw happening at the edges of that storm raised a brand new question about the atmosphere above it. Something bright was forming at the surface of the dark spot, something that moved faster than the storm itself, something that did not behave the way any storm cloud should. Chase a hurricane with a speedboat, and eventually the hurricane wins. Hurricanes on Earth move at about 15 to 30 miles per hour across the ocean's surface. Even a fast boat cannot keep up for long. The storm is bigger, more powerful, and it does not get tired. Now imagine a cloud system that chases a storm across an entire planet and laps it. That is exactly what scientists watched happening on Neptune. When Voyager 2 photographed the Great Dark Spot in 1989, scientists noticed something alongside it: a bright, white, compact cloud system sitting just to the south of the dark oval. It was moving faster than the storm, not by a little. It was lapping the Great Dark Spot every few days, racing completely around the planet and catching back up to the storm again and again. They nicknamed it the Scooter. To understand the Scooter, you have to think about altitude. On Neptune, different layers of the atmosphere move at different speeds. The deeper you go, the slower things move. The higher you climb, the faster things get. The Great Dark Spot sat at a middle altitude, spinning in the friction zone between two competing wind streams. The Scooter sat higher up, in a faster current. The Scooter was not being pulled along by the storm. It was riding a completely different river of wind, a higher, faster one. And as it moved, it was being shaped by the interaction between the atmosphere above and the storm system below. The Scooter appeared bright because it was made of methane ice clouds. Deep inside Neptune's atmosphere, methane gas gets pushed upward by convection currents. As it rises, it hits the cold upper atmosphere and freezes into tiny ice crystals. These crystals catch the faint light from the distant star and reflect it back. Against the dark blue of Neptune's lower atmosphere, they glow like white paint on a dark canvas. This same process creates most of the visible cloud features on Neptune. The bright streaks and patches you see in photographs of the planet are all made of methane ice, formed where fast-rising gas punches up into the cold upper layers and freezes. Scientists were fascinated by the Scooter because it was unusually compact and stable. Most methane ice clouds on Neptune form and dissolve quickly as the gas moves and the temperature shifts. The Scooter held its shape remarkably well while racing around the planet. After the Great Dark Spot disappeared, the Scooter was gone too. The two systems were connected in ways that scientists are still studying. Remove the storm below, and the cloud above loses its anchor. New bright cloud systems have appeared on Neptune since then. Some race around the planet in the same way the Scooter did. Scientists use them as tracers to measure wind speeds at different altitudes. By watching how fast a cloud moves compared to a feature below it, they can map the wind structure of the whole atmosphere layer by layer. And that map has revealed something disturbing. The wind does not just blow fast at the surface level. The speed changes dramatically as you go up or down through the atmosphere. Some layers move east, others move west. They grind against each other constantly, and in those grinding zones, the pressure builds. Something happens when that pressure gets extreme enough. The atmosphere does something completely unexpected with its color. Blue is not a common color in space. Stars burn white, yellow, orange, and red. Rocky planets are brown, red, and gray. Gas giants tend toward beige and tan, layered with yellows and browns. Jupiter is a swirl of orange and cream. Saturn is pale gold. Uranus is a muted pale blue-green, almost like old glass. Neptune is electric blue, deep, vivid, almost glowing. When you see a photograph of Neptune, that color feels deliberate, intentional, like someone chose it. And the reason for it comes down to chemistry happening in the atmosphere above you. Neptune's atmosphere is made mostly of hydrogen and helium, with a smaller but crucial amount of methane mixed in. Methane does something special with light. When sunlight, even the faint, weak sunlight that reaches Neptune, hits methane gas, the methane absorbs the red wavelengths, it soaks them up. And when red light gets removed from white light, what bounces back is blue. Uranus has methane too, and it also looks blue-green because of it, but Neptune is a distinctly deeper, more saturated blue. Scientists puzzled over this for years. Both planets have similar amounts of methane. Both are cold. Both sit in the outer solar system. So why does Neptune look so much more vividly blue? The answer is still being worked out, but the leading idea involves something else in Neptune's atmosphere that we have not yet identified. Some additional compound, Some unknown molecule is thought to be absorbing extra wavelengths of light and pushing the color deeper into the blue range. Scientists have called this mystery material simply the unknown absorber. It is one of many reminders that we have only visited Neptune once, and briefly, and from a distance. But the color is more than just beautiful. It is a reading of the chemistry happening across thousands of miles of atmosphere. Every shade variation in Neptune's blue tells scientists something about temperature, pressure, altitude, and the movement of gas beneath the cloud tops. The brightest white patches mark where methane ice clouds are forming. The darkest blue zones mark where the atmosphere is clearer, and you are seeing deeper into the planet. And the banding patterns, subtle stripes running roughly parallel to the equator, reveal the underlying structure of those supersonic wind currents below. Scientists can read Neptune's atmosphere the way a doctor reads a scan. The colors and patterns on the surface tell them what is happening miles below without ever going there. And what is happening below is something far stranger than frozen methane and blue light. The deeper you go into Neptune, the more extreme things become. Temperatures climb back up from the frozen upper atmosphere. Pressures increase to levels that do not exist anywhere on Earth. And the chemistry starts doing things that would be impossible in any normal environment. At a certain depth, the rules of how matter behaves start to bend. Something is happening down there that scientists first proposed decades ago and only recently started to confirm with laboratory experiments. Something that sounds like it belongs in a fantasy story. It rains diamonds inside Neptune. Most rain on Earth starts the same way. Water vapor rises, cools, condenses into droplets, and falls. Simple cycle. Repeat, the droplets are small, the fall is short, and they evaporate or pool somewhere and start over. Inside Neptune, something falls through the atmosphere that is a little harder to picture. Diamonds. Actual diamonds. Not metaphorical ones. Carbon atoms, under enormous pressure and heat, locking together into the hardest natural structure that exists in our world, and then falling downward through the planet's interior like a slow crushing hailstorm. Here is how it happens. Neptune's atmosphere contains methane. You already know that. Methane is a molecule made of one carbon atom bonded to 4 hydrogen atoms. In the upper atmosphere, methane behaves normally. It absorbs red light, contributes to Neptune's blue color, and drifts in the supersonic winds. But as you descend deeper into Neptune, something changes. Pressure increases, temperature rises, and at a certain depth, the pressure becomes so extreme that it starts to do something remarkable. It rips the methane molecules apart. The hydrogen atoms get separated from the carbon atoms. Now you have free carbon atoms floating in a high-pressure, high-temperature environment. Under those conditions, carbon does what it does under extreme pressure anywhere in the universe. It crystallizes. The atoms lock together in tight, regular lattice structures. They form diamonds. These diamonds are tiny. Scientists estimate they are probably small crystals, maybe a few millimeters or centimeters at most, but there are potentially enormous quantities of them forming constantly deep inside the planet. And once they form, they fall. Diamonds are denser than the surrounding fluid, so they sink. They drift downward through the planet's interior, toward the core, pulled by Neptune's gravity. Scientists believe this slow rain of crystals has been happening for billions of years, continuously, with no pause. A team at Lawrence Livermore National Laboratory tested this in a lab setting. They took a plastic material similar to the mixture of carbon and hydrogen found deep in Neptune, hit it with an incredibly powerful laser, and generated the extreme pressure and temperature conditions that exist inside the planet. Diamonds formed. The experiment worked. The diamond rain theory moved from idea to something much closer to confirmed. But the diamonds do not just fall harmlessly and disappear. Their descent does something important. As the crystals sink through the planet's fluid interior, they create friction. That friction generates heat. And that heat produced continuously by billions of tiny crystals falling through the planet's mantle over billions of years, may be one of the contributors to Neptune's mysterious internal energy output. The diamond rain might be helping power the storms. Think about that chain of events. Methane in the atmosphere breaks apart under pressure. Carbon crystallizes into diamonds. Diamonds fall. Falling diamonds generate heat. That heat rises. Rising heat drives convection. Convection feeds the supersonic winds. The supersonic winds power the storms. A planet literally running on diamond rain. And the deeper you go into Neptune, the more extreme the conditions get. The diamond rain is just one strange phenomenon happening beneath the cloud tops. Because below it, something else is waiting. A magnetic field so distorted and tilted that it should not function the way it does. Every planet with a magnetic field has something in common. The field roughly lines up with the planet's axis of rotation. Earth's magnetic north and its geographic north are close to each other. Not perfectly aligned, but close enough that a compass works reliably anywhere on the planet. Jupiter, Saturn, even Uranus, all of them have magnetic fields that stay reasonably close to their spin axis. Different strengths, different shapes, but the same basic orientation. Neptune's magnetic field does none of that. It is tilted 47 degrees away from the planet's rotation axis. To picture this, imagine if Earth's magnetic North Pole were not in the Arctic, but somewhere over the middle of the Pacific Ocean. Your compass would point in completely the wrong direction, depending on where you were standing. Navigation would be almost impossible. But the tilt is only part of the strangeness. On Earth, the magnetic field is generated by liquid iron moving in the planet's outer core. That movement, deep in the center of the planet, produces the field that wraps around the whole world. The center of Earth's field is very close to the physical center of the planet. Neptune's magnetic field does not originate near the center of the planet at all. Scientists believe Neptune's field is generated in the middle layers of the planet in a zone of electrically conducting fluid called an ionic ocean. This is a layer made of water, ammonia, and methane under such extreme pressure that the molecules break apart and the fluid carries electrical charge. When that charged fluid moves, it generates a magnetic field. But because the source is in the middle of the planet rather than the core, the field is offset. The center of Neptune's magnetic field sits millions of miles away from the center of the planet itself. The field does not wrap evenly around Neptune. It wobbles. It shifts. As Neptune rotates, the offset field sweeps through space in an uneven, lurching pattern. This creates something visually spectacular. On Earth, auroras form at the magnetic poles near the Arctic and Antarctic. They appear in rings around those poles because that is where the magnetic field funnels charged particles down into the atmosphere. The pattern is relatively predictable. On Neptune, the auroras can appear almost anywhere. Because the magnetic field is tilted and offset, the zones where charged particles enter the atmosphere shift constantly as the planet rotates. Auroras flash across the planet in irregular patterns, lighting up different latitudes, appearing and disappearing without any predictable rhythm. Neptune's auroras are a visual record of a completely chaotic magnetic environment, and that chaos does more than create light shows. The irregular magnetic field changes how energy from the distant star's solar wind interacts with the planet. Instead of being neatly funneled into predictable zones, energy gets dumped into the atmosphere at wild angles across much of the planet's surface. This feeds more energy into an atmosphere that is already receiving enormous amounts of heat from below. The magnetic field acts like an additional, unpredictable energy source, adding another layer of complexity to an already violent system. One planet. Internal heat from the deep interior. Diamond rain generating friction. A lurching magnetic field funneling energy from outside. 3 separate power sources, all feeding the same screaming atmosphere. And above all of this, in orbit around Neptune, something even stranger is happening. A moon is flying backwards. Moons follow rules. When a planet forms, it pulls material from the gas and dust swirling around it. That material settles into orbit and forms moons. The direction those moons orbit always matches the direction the planet is spinning. Always. It is a basic consequence of how planets and their moons form from the same rotating disk of material. Every large moon in the solar system follows this rule. Earth's moon goes the right way. Jupiter's 4 big moons go the right way. They all orbit in the same direction as their planet spins because they all formed from the same rotating disk of gas and rock. Triton goes the wrong way. Neptune's largest moon, with a diameter of about 1,600 miles, orbits in the opposite direction from Neptune's rotation. It flies backwards. And that backwards orbit is a signal so clear, so unmistakable, that it tells scientists exactly what happened. Triton did not form here. Triton was captured. It started its existence somewhere else, entirely. Out past Neptune, in the region called the Kuiper Belt, billions of small icy objects orbit slowly in the dark. They are the leftovers from the formation of the solar system. Cold, slow, ancient. Triton was once one of them. At some point in the early history of the solar system, Triton drifted too close to Neptune. Neptune's gravity caught it. This was not a gentle process. A capture event on this scale would have been catastrophic. Triton would have been torn, twisted, and decelerated by Neptune's gravitational pull. It may have collided with other moons that were already orbiting Neptune at the time, destroying them. Its new orbit would have been wildly elliptical, swinging close to Neptune and then far away in a chaotic, unstable path. Over millions of years, tidal forces slowly shaped that chaotic orbit into a circle. Neptune's gravity kneaded Triton's orbit smooth, like working dough, but nothing could change the direction. Triton still orbited backwards because it arrived going the wrong way, and physics has no mechanism to flip that. Today, Triton orbits Neptune in a near-perfect circle, about 220,000 miles out. From a distance, it looks calm and stable, but that orbit is a death sentence. And here is the reason. A backwards orbit inside a planet's gravitational field loses energy over time. The tidal interaction between Triton and Neptune is slowly draining Triton's orbital energy. Every year, Triton's orbit shrinks by a tiny, almost immeasurable amount. It moves closer to Neptune, slowly, steadily, with no way to stop. The math has been done. In roughly 3.5 billion years, Triton will cross the line where Neptune's gravity becomes too strong for a moon to survive. At that point, something violent and spectacular will happen. But before we get to the destruction of Triton, there is something else this moon is doing right now. Something that should be impossible on a moon that cold, that far from any heat source. Triton's surface is erupting. A moon covered in nitrogen ice, sitting at negative 390 degrees Fahrenheit, should be completely still. Cold stops things. Cold slows molecules down, freezes liquids solid, and shuts down any geological activity. A moon that cold, that far from its star, with no significant internal heat of its own, has no business producing any kind of eruption. Triton does it anyway. When Voyager 2 flew past Neptune in 1989 and turned its cameras toward Triton, scientists expected a smooth, frozen, geologically dead world. What they saw instead were dark streaks extending across the surface of the southern polar cap. Streaks that started at specific points and trailed off in the same direction like smoke from individual chimneys, all blowing the same way in the wind. They were looking at geyser plumes. Triton has geysers, active, erupting geysers that shoot dark material miles into the extremely thin atmosphere. Scientists spent weeks analyzing the images and trying to figure out what was powering them, because the obvious answer, internal heat, did not seem available to a moon this cold. The answer they settled on is elegant and strange. Triton's south polar cap is covered in nitrogen ice, and it is exposed to extremely faint sunlight for much of Triton's long summer. That sunlight, even at Neptune's distance, carries just enough energy to do something unusual. It passes through the transparent layers of nitrogen ice near the surface and gets absorbed by darker material underneath. That heat, trapped under the ice like a greenhouse, warms the nitrogen from below. As the nitrogen warms, it turns to gas. The gas pressure builds beneath the surface. Eventually, it finds a weakness and erupts upward, punching through the ice and launching a plume of dark nitrogen gas and dust miles above the surface. The geysers then trail off in the direction of Triton's wind, which, though extremely thin, is enough to push the material into long, dark streaks across the bright polar cap. Voyager 2 photographed at least 8 of these active geysers during its flyby. Scientists believe the southern polar cap is covered in hundreds more, a moon powered by sunlight so faint that it would not even cast a shadow on Earth, erupting in geysers visible from space. But Triton's strangeness goes deeper than its surface. The moon has a varied, complex landscape that surprised everyone who studied the Voyager images. There are smooth plains, ancient craters, and a bizarre terrain scientists call cantaloupe terrain, a region of bumpy, irregular hills covering a large part of the northern hemisphere and looking exactly like the skin of a cantaloupe melon. This terrain is unique in the solar system, and scientists still debate what formed it. Triton is also thought to have a subsurface ocean of liquid water, kept liquid by tidal heating from its interaction with Neptune's gravity. If that is correct, Triton joins a growing list of moons in the outer solar system that may harbor liquid water beneath their frozen surfaces. And that moon, ancient and strange, with its geysers and its buried ocean, is drifting slowly toward its end. But there is still something wilder ahead. What happens when Triton finally arrives? 3.5 billion years from now, something extraordinary will happen in the skies around Neptune. Triton will cross a boundary called the Roche limit. This is the distance from a planet where tidal forces become too powerful for a smaller body to hold itself together. Inside the Roche limit, the difference in gravitational pull between the near side and far side of a moon is so extreme that the moon cannot stay in one piece. Triton will be torn apart. The process will not be instant. It will take millions of years. Triton will begin to crack and fracture as the tidal forces exceed what the moon's own gravity can resist. Pieces will break away. Smaller chunks will separate. Over time, the entire moon will be shredded into billions of fragments. Those fragments will spread out along Triton's orbit, and because Triton currently orbits Neptune in a tight, near-circular path, those fragments will form a ring. Scientists have calculated what that ring might look like. Triton contains enough material that the resulting ring system would dwarf anything currently orbiting Neptune. It would likely rival and possibly exceed Saturn's rings in terms of mass. A ring system that stretches tens of thousands of miles from Neptune, made of the shattered remains of a moon that once wandered in from the Kuiper Belt. Billions of years earlier, the death of Triton will transform Neptune into the most visually spectacular planet in the solar system. But we will not be here to see it. 3.5 billion years is longer than Earth has existed. The timescales involved are almost impossible to hold in your mind, and yet the math that predicts this outcome is solid. Scientists are confident in the trajectory. Triton's orbit is shrinking measurably. The moon is on a timer that has been running since the day Neptune captured it. From our perspective today, Triton looks stable. It orbits quietly, erupts its geysers, holds its frozen surface at temperatures that make Antarctica feel tropical. Nothing about it looks like a countdown. But the countdown is real, and here is something that makes this more than just a distant abstract fact about a moon we will never visit. The destruction of moons and the formation of ring systems is a process that explains where many of the rings we see in the solar system came from. Saturn's rings, which look so ancient and permanent, are actually geologically young. Scientists believe they formed relatively recently, possibly within the last few 100 million years, from the destruction of an earlier moon or comet. What we see at Saturn is the aftermath of exactly the kind of event heading toward Neptune. Rings are not permanent features. They form from destruction, and they fade over time as particles drift inward or outward and spread too thin. Neptune's current rings are faint and barely visible, but they already hint at a violent history, and they point toward a violent future. Before we get to that future, though, there is something strange happening to Neptune right now. Something that started showing up in telescope data in the last few years. Something that should not be happening if our models of this planet are correct. Neptune is cooling down. And nobody knows why. In 2018, a team of scientists decided to take the most detailed temperature reading of Neptune's atmosphere ever attempted. They gathered data from multiple telescopes around the world and pieced it together into a picture of Neptune's thermal glow, the heat the planet radiates at different layers of the atmosphere. They expected to find something relatively stable. Neptune's temperature had been measured before. The numbers seemed settled. The data came back, and something was wrong. Neptune's upper stratosphere, the layer of atmosphere above the main cloud deck, had dropped in temperature significantly since the first careful measurements were taken in 1989. The drop was roughly equal to 17 degrees Fahrenheit over about 20 years. That sounds small, but at Neptune's temperatures, it is enormous. The stratosphere had lost a significant fraction of its total heat. The planet was cooling. Scientists ran through the expected explanations. Neptune is tilted on its axis, like Earth, which means it experiences seasons. As the seasons change, the amount of direct energy hitting each hemisphere shifts. Maybe the cooling was just seasonal, a normal fluctuation. The timing did not match. Seasonal models predicted Neptune's southern hemisphere should have been warming during this period, as it was heading into a long southern summer. It was cooling instead, the opposite of what was expected. There was another possible explanation. The star at the center of our solar system goes through cycles of activity roughly every 11 years. During high activity, it sends out more energy, including ultraviolet light that can heat the upper atmospheres of planets. During low activity, less energy goes out. Maybe Neptune was responding to a down cycle in solar activity. Scientists tested that explanation too. The cooling was too large, too fast, and started at the wrong time relative to the solar cycle to be explained by it, which left an uncomfortable answer sitting in the middle of the data. Something is happening inside Neptune's upper atmosphere that we do not understand. The internal heat engine, the diamond rain, the convection currents, all of that operates deep inside the planet and in the lower atmosphere. The cooling observed was at the very top of the atmosphere. Whatever is causing it is happening in a place we have the least understanding about. Some scientists have proposed that changes in chemical composition in the upper atmosphere might be altering how efficiently it radiates heat into space. Others have suggested that changes in cloud cover could be exposing more of the upper atmosphere to the cold of space. None of these ideas has been confirmed. None of them fully explains the numbers. Neptune is the only planet in our solar system that has been visited by a spacecraft exactly once, briefly from a distance of about 3,000 miles, over 30 years ago. Almost everything we know about Neptune since then comes from telescopes that cannot see through its clouds or probe its interior. We are reading one of the most violent and complex planets in existence from billions of miles away, with limited tools, and the planet keeps sending back data that does not fit our models. And deep inside that planet, underneath all the cooling and the storms and the magnetic chaos, something is pressing down on everything, the weight of a world collapsing on itself. Most of what you see of Neptune is atmosphere. From space, the planet looks like a solid sphere, deep blue, smooth, complete. But Neptune has no solid surface to stand on. What you are looking at is gas. Thousands of miles of gas pressing down on more gas, pressing down on liquid, pressing down on something even denser below. As you descend into Neptune, the pressure rises continuously. At the top of the atmosphere, the pressure is low, similar to the upper atmosphere on Earth. But every mile you descend, more atmosphere is stacked above you. The weight compounds. The pressure climbs. By the time you reach the lower atmosphere, the pressure is already crushing by any standard you could apply on Earth. But you keep going down. Below the atmosphere is a layer scientists call the ice mantle. The word ice here is misleading. At these depths, the temperature is thousands of degrees Fahrenheit, and the pressure is millions of times greater than what you feel at sea level on Earth. The water, ammonia, and methane in this layer are not frozen in the way you would think of ice. They are a hot, pressurized, electrically conducting fluid. The molecules are packed so tightly and compressed so powerfully that they behave like nothing in everyday experience. This is the layer where the diamonds are forming, where carbon atoms get ripped from methane and crystallize under the extreme pressure, where the diamonds fall downward through the fluid and generate the friction that contributes to Neptune's internal heat. And this is also the layer where Neptune's magnetic field is being generated as that hot, electrically charged fluid swirls and moves, creating the tilted offset field that wraps around the whole planet in that chaotic wobbling pattern. Below the ice mantle, scientists believe there is a core, a dense ball of iron, nickel, and silicate rock, roughly the size of Earth, sitting at the center of the planet. The pressure at the core is beyond anything that can be easily described. Every atom in that core is being pressed against its neighbors with a force that would crush any material we know of into unrecognizable forms. The core temperature is thought to reach around 9,000 degrees Fahrenheit, hotter than the surface of many stars. And yet this heat, sitting at the very center of the planet, has to make its way outward through thousands of miles of dense, pressurized fluid before it can affect anything we can observe. The journey from the core to the clouds above takes the energy through multiple layers, each one adding complexity, each one contributing to the system in its own way. By the time that energy reaches the upper atmosphere and starts driving the supersonic winds and generating the storms, it has traveled through one of the most extreme environments in the solar system. This entire interior, from the rocky core to the ice mantle to the lower atmosphere, is a machine built from pressure and heat and chemistry that we have never directly observed and may never be able to reach. And that machine has been running for 4.5 billion years without stopping. The full scale of what Neptune is becomes clearer when you try to hold all of it together at once. Rocky core under extreme pressure, diamond rain falling through hot fluid, magnetic field generated by electrically charged oceans, supersonic winds at the top, storms the size of Earth appearing and vanishing. But one piece of this picture is still missing. The one question underneath all the others. Why does Neptune produce so much more heat than it receives? The diamonds help. The cooling interior helps, but neither adds up to the full number. Something else is going on. Something we have not yet named. Stand outside on a clear night and look up. Every star you see is burning, producing heat, sending energy outward in all directions. Planets catch a small fraction of that energy and warm up. That is the basic deal. Stars give, planets receive. Neptune is breaking that deal. The numbers are measured and confirmed. Neptune takes in a certain amount of energy from its distant star. Then scientists measure how much heat Neptune radiates back out into space. The output is about 2.5 times the input. Every measurement, from every telescope that has looked at this carefully, comes back with the same result. Neptune is producing roughly 1.5 times more heat than it receives. Extra heat that has to come from somewhere. You already know 2 of the candidates. The residual warmth left over from Neptune's violent formation 4.5 billion years ago, slowly leaking outward like a cooling ember, and the diamond rain generating heat through friction as crystals fall through the fluid interior. Neither one is enough on its own. Scientists have modeled what the cooling of Neptune's interior from formation should look like over 4.5 billion years. The planet should have lost most of that original heat by now. Some of it should remain, but probably not enough to account for the full surplus. The diamond rain is harder to quantify. The rate at which diamonds form, fall, and generate heat is estimated, based on lab experiments and computer models. The contribution is real, but scientists cannot measure it directly from Earth or from orbit. The estimate has a large range of uncertainty. Added together, these two sources might explain the measured heat output, or they might fall short, or some combination with a third source, still unidentified, might be the real answer. One proposal that has attracted serious attention is related to the Roche limit story of Triton. When Neptune captured Triton billions of years ago, that capture event was violent. Triton's original orbit was highly elliptical and chaotic. Neptune's tidal forces worked on Triton to circularize that orbit over millions of years. And tidal forces generate heat. The energy extracted from Triton's orbit had to go somewhere. Scientists believe a significant portion went into Neptune's interior, adding to the planet's heat budget. If true, the capture of Triton billions of years ago is still heating Neptune today. A moon that was grabbed from the outer solar system, forced into a backwards orbit, and slowly circularized, is still paying a thermal debt to the planet that caught it. That idea connects events separated by billions of years into a single story. Neptune grabbed Triton. Triton's orbit released energy into Neptune. That energy has been slowly working its way out through the interior ever since, contributing to the excess heat that powers the winds and storms above. But scientists are careful. This is a compelling idea. The numbers are plausible, and it remains for now an explanation that fits the evidence, rather than a proven fact. The honest answer is that we do not fully know where Neptune's extra heat comes from. We have visited Neptune exactly once, briefly, decades ago, and that visit, as extraordinary as it was, barely scratched the surface of what this planet is hiding. August 25th, 1989. That is the date humanity came closest to Neptune. A spacecraft called Voyager 2, launched 12 years earlier, curved around the planet at a distance of about 3,000 miles from the cloud tops. 3,000 miles! From Earth, Neptune is 2.8 billion miles away. That flyby was the closest any human object has ever been to this planet, before or since. Voyager 2 was not designed specifically for Neptune. It was built for a grand tour of the outer solar system, taking advantage of a rare alignment of the planets that allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity to slingshot toward the next. That alignment happens once every 175 years. Scientists in the 1960s calculated the window and made sure Voyager 2 was ready. The flyby of Neptune lasted a matter of hours at close range. Everything the spacecraft could observe, it observed simultaneously. Multiple instruments ran at once. Cameras captured images. Magnetometers measured the magnetic field. Infrared sensors measured heat. Radio signals probed the atmosphere. And then Voyager 2 was gone. It could not slow down. Stopping at Neptune was never an option. The spacecraft was moving at tens of thousands of miles per hour, using Neptune's own gravity to redirect its path. And then it was past the planet and heading out into interstellar space. In those few hours, scientists gathered more direct data about Neptune than in all the decades of telescope observation before and after. They discovered the Great Dark Spot, they measured the wind speeds, they mapped the magnetic field, they photographed Triton's geysers, they counted rings, they discovered 6 new moons in the data, all of it from a window of hours. Since then, every piece of new information about Neptune has come from telescopes. The Hubble Space Telescope watched the Great Dark Spot disappear and spotted new storms forming. Ground-based observatories tracked temperature changes, space telescopes measured heat output, but no spacecraft has gone back. The distance is the main reason. A mission to Neptune requires years of travel. Voyager 2 took 12 years, and it was on an optimized trajectory using gravity assists from multiple planets. A dedicated Neptune mission following a more direct path would take a similar amount of time, with a spacecraft that would need to carry enough fuel to actually slow down and enter orbit, rather than just fly through at high speed. Entering orbit changes everything. A spacecraft in orbit around Neptune could study the planet continuously for years. It could dip into the upper atmosphere. It could closely observe Triton. It could measure the magnetic field continuously as the planet rotates, mapping its full three-dimensional structure. Scientists have proposed such a mission multiple times. The technology exists in concept, the scientific case is strong. Neptune and Uranus have been formally identified as the highest priority targets for the next major planetary mission in official planning documents. But as of now, no mission has launched. Neptune sits out there, running on its internal engine, tearing through its own atmosphere at supersonic speeds, slowly pulling Triton toward destruction, cooling in ways we do not understand. And we have not gone back. Everything you have learned about this planet so far came from a few hours of data 35 years ago and a set of telescopes trying to read a planet from billions of miles away. The strangest discoveries about Neptune may still be waiting. Triton gets all the attention, and for good reason. It is enormous compared to everything else orbiting Neptune. It is geologically active. It is flying backwards. It is doomed. Triton is the dramatic centerpiece of Neptune's moon system, and it dominates nearly every conversation about what orbits this planet. But Neptune has 15 other known moons, and the story of those moons is in its own quiet way just as strange as Triton's. Most of Neptune's smaller moons orbit close to the planet, inside or near the ring system. They are small, irregularly shaped, and dark. So dark, in fact, that several of them were not discovered until Voyager 2 flew past in 1989 and its cameras picked them up at close range. From Earth, they were invisible against the glare of the planet. The largest of the inner moons is called Proteus. It is a lumpy, roughly potato-shaped object, about 260 miles across. Scientists believe Proteus should be large enough for gravity to pull it into a sphere, but it is not quite there. It sits just at the edge of the size where gravity wins that battle against the strength of the rock itself. Proteus orbits Neptune faster than Neptune rotates, completing a full orbit in just over one Earth day. Here is where it gets strange. Triton, the giant backwards moon falling inward, and Proteus, the smaller forward-orbiting moon sitting closer to Neptune, are on a slow collision course of sorts. As Triton spirals inward over billions of years, it will eventually reach the region where Proteus currently orbits. What happens at that point is uncertain. The gravitational interaction could eject Proteus entirely, send it crashing into Neptune, or simply destabilize its orbit enough to cause a cascade of collisions among the inner moons. Triton is not just doomed itself. Its doom may doom everything else orbiting close to Neptune. Further out, beyond Triton, Neptune has a collection of small, irregular moons. These are objects that orbit far from the planet, in tilted and elliptical paths, sometimes in the forward direction and sometimes backward. Scientists believe most of these outer irregular moons were captured by Neptune's gravity in the early solar system, the same way Triton was, just much smaller and less dramatically. They are ancient prisoners, remnants of a violent early period when the outer solar system was a chaotic place of collisions, captures, and ejections. And studying them reveals something important about Neptune's history. The presence of so many irregularly orbiting moons, objects that clearly did not form in place, tells scientists that Neptune went through a particularly turbulent youth. The planet may have migrated significantly from its original position in the solar system, moving outward through the disk of material and sweeping up moons, disrupting the orbits of everything nearby, and settling only gradually into its current position, 30 times farther from the star than Earth. Neptune's moon system is a frozen snapshot of that chaotic past. Each moon is a survivor, or a prisoner, depending on how you look at it. And circling all of these moons, threading between them, sitting right at the boundary between the inner and outer systems, are Neptune's rings, faint, dark, and hiding a history of their own. For most of the 20th century, scientists assumed Neptune had no rings. Jupiter had rings, discovered in 1979. Saturn's rings were famous. Uranus was found to have rings in 1977, when it passed in front of a distant star, and the star's light flickered before and after the planet blocked it, revealing the ring material on either side. Scientists tried the same technique with Neptune multiple times. They watched Neptune pass in front of stars. Sometimes the star's light dimmed slightly before Neptune reached it. Sometimes it did not. The results were inconsistent, confusing. Unlike Uranus, where the dips in starlight were symmetric and clean on both sides of the planet, Neptune's signal was messy. One astronomer proposed a solution that seemed almost absurd at the time. What if Neptune's rings were not complete? What if instead of continuous bands of material circling the planet, Neptune had arcs, partial rings, sections of ring material that existed in some locations along the orbit but not others? Complete rings made physical sense. Partial arcs did not. Ring particles should spread out over time and fill the entire orbit. A stable arc should not exist. Gravity should distribute the material evenly. An arc is just a ring in the process of spreading out, and it should complete itself quickly by planetary timescales. And yet that is exactly what Voyager 2 found in 1989. Neptune has rings, and they are clumped. The rings contain distinct arcs, regions of much higher particle density, separated by sections where the ring is almost empty. The arcs have names. The most prominent are called Liberté, Égalité, and Fraternité. Scientists scrambled to explain how these arcs could exist. The answer came from one of Neptune's inner moons. A small moon called Galatea orbits just inside the main ring. As Galatea orbits, its gravitational pull interacts with the ring particles in a specific resonance pattern. The timing of Galatea's orbit relative to the ring particles creates zones where particles are nudged back into line if they drift, and swept out if they end up in the wrong place. This gravitational corralling keeps the material bunched into arcs rather than spreading smoothly around the orbit. Galatea is essentially herding the ring particles, keeping them in clumps. But this system is not stable forever. The resonance that keeps the arcs together is sensitive. Small changes in the orbits of the moons involved could disrupt it, and observations from the Hubble Space Telescope over the decades since Voyager 2's visit have shown that the arcs are indeed changing. They are shifting and fading. Particles are slowly escaping the resonance zones. The arcs are spreading. Neptune's rings, already some of the darkest in the solar system, made of material as black as coal, are slowly dissolving. And as the rings fade and the arcs disperse, scientists are left wondering what created them in the first place. The material in the rings had to come from somewhere. The leading idea is that it came from the collision or breakup of earlier moons, smaller bodies that were struck by passing objects and shattered into the fragments now circling the planet. Neptune's rings are rubble, the remains of moons that did not survive. And studying that rubble has started to give scientists clues about what the environment around Neptune looked like billions of years ago, when the outer solar system was still being assembled. The picture that emerges is one of remarkable violence. 4.5 billion years ago, the solar system was unrecognizable. A vast rotating disk of gas and dust swirled around a newly formed star. Clumps of material were sticking together, growing larger, colliding, breaking apart, and colliding again. The process was chaotic and slow by human standards, but relentless. Planets were assembling themselves from the chaos. Neptune was forming far out in this disk, in the cold outer region where ice could survive. It pulled in material steadily, growing from a small rocky core into a world of ice and gas. But the region where Neptune sits today, 30 times farther from the star than Earth, may not be where Neptune formed. Scientists studying the early solar system have built models of how the gas giant planets migrated in the early period of solar system history. Those models, particularly a framework developed by researchers in Nice, France, and known as the Nice model, suggest that the giant planets formed closer together and then moved outward over time. Jupiter and Saturn's gravitational interactions with each other, and with the disk of material around them, sent ripples through the whole system. Uranus and Neptune were pushed outward. Neptune may have originally formed much closer to the star, possibly in a region closer to where Uranus sits today. Over tens of millions of years, it migrated outward, sweeping through the outer disk of material as it moved. This migration would have been catastrophic for anything in its path. Objects in the Kuiper belt were scattered, some were thrown inward, sending a shower of icy bodies crashing into the inner planets. Some were ejected entirely from the solar system. Some were captured by Neptune. Triton was probably captured during or shortly after this migration. This violent migration period explains a lot of what we see in the outer solar system today. The composition of Neptune's current irregular moons matches what we would expect from captured Kuiper belt objects. The structure of the Kuiper belt itself, with its complex distribution of orbits and sizes, shows the sculpting effect of Neptune's passage through it. Neptune is not sitting peacefully at the edge of the solar system. It is sitting where it landed after billions of years of migration, collision, and gravitational chaos. The calm blue sphere we see today is the aftermath of one of the most violent journeys any planet in our solar system has taken. And that migration changed the solar system in ways we are still mapping. The bombardment of the inner planets triggered by Neptune's movement may have been the same period that delivered water to Earth. The icy bodies scattered inward from the Kuiper belt may have brought the building blocks for life to the inner solar system. Neptune's violent youth may be connected indirectly to the existence of everything living on Earth today. That connection, stretching from a distant blue planet to the water in your body, is one of the most striking things in planetary science. A planet 4.5 billion miles away, moving through the early solar system, throwing ice at the young Earth. And what that planet became after all that chaos is something even harder to explain. Because even now, settled in its orbit, Neptune is doing something that no model of planet formation fully predicted. It is running hotter than it should ever be. You have heard about the winds. You have heard about the storms. Now step inside one. Imagine dropping into Neptune's upper atmosphere. The first thing you would notice is the color, deep blue in every direction. The sky above you, the gas below you, all the same vivid electric blue. There is no ground, no horizon line, just gas extending in every direction as far as anything could reach. The wind hits you immediately, 1,300 miles per hour. The comparison is almost useless because there is nothing in everyday life to reference it against. The fastest a commercial airplane flies is about 575 miles per hour. Neptune's wind is more than twice that. You would not feel it as a breeze or a gust. You would be accelerating instantly, carried along at supersonic speed before your brain could register what was happening. The temperature is negative 360 degrees Fahrenheit around you, cold enough that most gases would freeze solid on Earth. But Neptune's atmosphere is so high up and so low in density that it does not behave like a thick, cold blanket. It is more like a thin, screaming river of gas racing around the planet. Moving deeper, pressure increases. The color begins to shift. The clear blue above gives way to thicker cloud layers. These are the methane ice clouds, the same ones that form the bright streaks visible from telescopes on Earth. Inside them, visibility drops to almost nothing. The ice crystals are tiny, too small to see individually, but packed together they create something like an extreme fog moving at 1,000 miles per hour. Below the methane ice clouds, scientists believe there are deeper cloud layers. Water and ammonia may condense into their own cloud decks at lower altitudes. similar in some ways to how Earth's lower atmosphere layers into different kinds of clouds at different heights. These deeper layers have never been directly observed. Scientists infer their existence from the temperature and pressure profiles measured by remote instruments. Deeper still, the atmosphere transitions into the ice mantle. The gas gives way to hot fluid. The temperature is rising now, climbing back toward the extreme heat of the interior. Pressure has become extreme enough that the fluid conducts electricity. And in this fluid, storms are born. The convection currents here are enormous. Hot fluid rises from below, cooler fluid sinks from above. The meeting of these currents creates rotational movement. That movement at Neptune's scale becomes a vortex. The vortex grows, fed by the continuous heat from below, until it punches upward through the fluid layers and erupts into the atmosphere as a dark spot visible from billions of miles away. Then it dies. The energy that built it is consumed. The currents that fed it shift. The upper atmosphere tears it apart with its relentless shearing winds. The storm dissolves back into the atmosphere. The whole cycle, birth to death of a storm that could swallow Earth, might take just a few years. And somewhere in that cycle, in those winds and those clouds and those rising currents, something else is happening. Neptune's atmosphere is producing chemical reactions we have barely begun to catalogue. Complex organic molecules may be forming in the upper atmosphere, where ultraviolet light from the distant star strikes methane and hydrogen. On other planets, this kind of chemistry is considered a precursor to the building blocks of life. Nobody is suggesting life exists in Neptune's atmosphere, but the chemistry is happening, and the next chapter asks a question that changes how you think about this whole planet. The question sounds absurd at first. Neptune is a world of supersonic winds, crushing pressure, temperatures colder than anything on Earth, and storms big enough to swallow continents. Every standard definition of a habitable environment rules Neptune out completely, and yet scientists have learned over the past few decades that life on Earth is far more adaptable than anyone assumed. Organisms called extremophiles survive in environments that should kill them. Bacteria live in the boiling water around deep-sea volcanic vents, where temperatures exceed 200 degrees Fahrenheit and pressure would crush any surface animal. Other organisms survive in highly acidic environments, in the coldest regions of Antarctica, in solid rock miles underground, in water with almost no oxygen. Life on Earth keeps showing up in places where it has no business surviving. So scientists have started asking a different kind of question about places like Neptune. Instead of asking whether Neptune could support Earth-like life, they ask whether any conceivable chemistry could organize itself into a self-sustaining system under Neptune's specific conditions. The upper atmosphere of Neptune, high above the crushing lower layers, has temperatures and pressures that are actually less extreme than the deep interior. Around 30 miles below the outermost cloud tops, temperatures and pressures reach ranges that are harsh, but not uniquely impossible. Some researchers have pointed to this zone as theoretically interesting, not because life is expected there, but because the chemistry at that altitude is complex and energy is flowing through it continuously. Organic molecules are forming in Neptune's upper atmosphere. The ultraviolet light from the distant star drives chemical reactions in the methane and nitrogen. These reactions produce compounds called tholins, dark reddish organic materials that coat the surfaces of many cold outer solar system bodies. Tholins are considered prebiotic chemistry. They are not life. They are some of the raw ingredients that, under the right conditions, might lead toward it. On Neptune, those ingredients form in the upper atmosphere and then get carried downward by gravity and circulation into the deep crushing layers below. Any complex chemistry they represent is destroyed long before it could organize into anything meaningful. But this matters for a different reason. The same chemistry happening in Neptune's atmosphere happens in the atmospheres of planets orbiting other stars. Gas giants with thick hydrogen and methane atmospheres, heated by their own internal energy, producing organic chemistry in their upper layers, Scientists use Neptune as a model to understand those distant planets. What happens in Neptune's atmosphere gives them predictions to test when they study exoplanets with telescopes. Neptune, for all its violence and its distance, is a laboratory. And what scientists learn from it applies to hundreds of worlds we are just beginning to discover beyond our solar system. Which raises the most ambitious question in this entire story. What can Neptune teach us about finding planets that could actually support life? In the last 30 years, astronomers have confirmed the existence of thousands of planets orbiting other stars. The methods used to find them mostly involve measuring tiny dips in starlight when a planet passes in front of its star, or measuring tiny wobbles in a star's movement as a planet's gravity tugs on it. These methods reveal the size and mass of a planet, and sometimes a rough estimate of its distance from its star. They rarely reveal what the planet is actually like. But here is the problem. When scientists look at the catalogue of known exoplanets, one category shows up again and again with surprising frequency. Planets roughly the size of Neptune and Uranus, sometimes called ice giants, appear to be extremely common across the galaxy. They may be one of the most abundant types of planet in existence, and we have almost no idea how they work. Earth is studied in exhaustive detail. Mars has been visited by dozens of spacecraft. Jupiter and Saturn have had dedicated orbiters circle them for years, returning massive amounts of data. But ice giants like Neptune are almost completely unexplored. The single flyby of Neptune by Voyager 2 is all the direct data humanity has from an ice giant planet. Everything else is inference, modeling, and telescope observation from billions of miles away. This creates a serious gap. If ice giant planets are extremely common, and if scientists want to understand what those planets are like, what their atmospheres contain, how they generate heat, what their magnetic fields do, then Neptune is the closest and most accessible example available. It is the template, the reference point. Every model scientists build to interpret the light coming from a distant ice giant exoplanet is based in part on assumptions derived from what little we know about Neptune. If those assumptions are wrong because our Neptune data is incomplete, then our interpretation of the exoplanet data is wrong too. Getting Neptune right matters far beyond the solar system. There is a specific type of exoplanet that has received enormous attention from scientists searching for signs of life. These are planets in the habitable zone of their star, where liquid water could exist on the surface. Most of the planets found in habitable zones so far are larger than Earth, but smaller than Jupiter. Many of them fall into the size range close to Neptune. Understanding whether those planets have thick hydrogen and methane atmospheres, rocky surfaces buried under crushing gas, magnetic fields that protect or expose their surfaces to radiation, all of that depends on understanding Neptune's internal structure and dynamics. A dedicated Neptune orbiter mission would not just answer questions about one planet, it would recalibrate how scientists read hundreds of planets orbiting distant stars. The stakes of going back to Neptune are enormous, and the mission that scientists have been designing for decades, a mission that would enter orbit, study the planet continuously, and drop a probe into the atmosphere to measure it directly, remains one of the most scientifically compelling proposals in planetary science. Whether it will happen is a question of funding, priority, and time, but the scientific case grows stronger every year, because every time scientists look more carefully at Neptune, they find something new that does not fit what they expected. Weather on Earth runs on a simple fuel source. The star heats the surface heats the air, warm air rises, cold air sinks, and the whole global circulation machine spins up from that basic energy input. Every hurricane, every jet stream, every monsoon season traces back to the same root cause: heat from below, transferred to the atmosphere above. Neptune's weather system runs on multiple fuel sources simultaneously, and the interaction between those sources creates a level of complexity that Earth's weather cannot match. You have the internal heat engine pumping energy upward from the deep interior. You have the diamond rain generating additional friction and heat as crystals fall through the mantle. You have the tilted, offset magnetic field channeling energy from the solar wind into the atmosphere at unpredictable locations. You have the extreme temperature difference between the hot interior and the frozen upper atmosphere, driving powerful convection. All of these are feeding energy into the same atmospheric system at the same time. On Earth, meteorologists struggle to predict the weather 10 days out. The system is complex enough with a single dominant energy source that long-range prediction remains fundamentally difficult. Small errors in the starting conditions produce wildly different forecasts just a week or two later. Neptune's atmosphere has 4 separate energy inputs, each one operating on different timescales at different depths with different spatial patterns. The interactions between them are staggering in complexity. A surge in internal heat from below might trigger a convection event that produces a new storm. That storm might interact with the magnetic field energy input and grow in an unexpected direction. The shearing winds above might tear it apart before it becomes visible, or they might not. Scientists modeling Neptune's atmosphere run into a fundamental problem. They cannot gather the starting conditions needed for accurate modeling. The atmosphere is too deep, too remote, and too complex to measure at sufficient resolution from Earth. What they can do is study the behavior of the atmosphere at the levels visible from telescopes and work backward to understand the processes below. Observing how storms form, grow, and die tells scientists something about the convection structure below. Watching how cloud systems move at different altitudes maps the wind structure. Tracking the temperature changes in the stratosphere probes the energy balance of the whole system. Each observation is a clue, and the picture those clues have built over decades of telescope watching is of a weather system far more dynamic, far less predictable, and far more extreme than anyone imagined when Neptune was first discovered. A planet that should be frozen and still, running a weather machine of extraordinary violence and complexity. And that violence has a rhythm to it. Scientists have noticed patterns in Neptune's storm activity that seem to follow cycles. New storms tend to appear at certain latitudes. The interaction between major storm systems and the background wind follows recognizable patterns. The atmosphere seems to organize itself at least partially, despite the chaos. Understanding that organization is one of the key goals of future Neptune research, because that organization, that self-structuring behavior of a complex atmosphere under extreme conditions, might be telling scientists something profound. Something about how all planets, including Earth, organize their weather from the chaos of physics. Somewhere in a building at NASA or the European Space Agency, a document exists. It describes a spacecraft, a machine designed to travel billions of miles, slow down enough to enter orbit around Neptune, release a probe into the atmosphere, and then spend years circling the planet, watching, measuring, and transmitting data back to Earth. The mission has gone by various names at various stages of planning. Scientists have debated its instruments, its trajectory, its power source, and its scientific priorities for decades. It represents the most ambitious planetary mission currently on the drawing board, and it has not launched yet. The main technical obstacle is power. At Neptune's distance from the star, solar panels are useless. The light is too faint to generate meaningful electricity. Voyager 2 was powered by radioisotope thermoelectric generators, devices that convert heat from decaying radioactive material into electricity. A Neptune orbiter would need the same kind of power source, scaled up significantly to run a full suite of science instruments for years. The trajectory is another challenge. Getting a spacecraft to Neptune requires either an extremely long direct flight, taking over a decade, or a carefully planned series of gravity assists using the planets along the way to build up speed. These gravity assist opportunities are rare. They depend on the alignment of the planets, and the right alignment might not occur for years after a mission is approved and built. And then there is the question of slowing down. Voyager 2 flew through at high speed, and kept going. An orbiter has to slow down enough to be captured by Neptune's gravity. That requires carrying a large amount of fuel, which adds weight, which requires a bigger launch vehicle, which increases cost. None of these obstacles is insurmountable. Scientists have solved harder problems, but each one adds to the time and cost of the mission, and planetary missions compete for a limited budget. The scientific return, however, would be extraordinary. An orbiter could map Neptune's gravitational field precisely enough to reveal the internal structure of the planet. It could track storms through their entire life cycles. It could measure the magnetic field continuously through hundreds of rotations, building a complete three-dimensional model of how the field is generated and how it shifts. It could observe Triton closely enough to confirm whether a subsurface ocean exists. A probe released into the atmosphere could descend through the cloud layers and directly measure temperature, pressure, chemical composition, and wind speed at each altitude. For the first time, scientists would have ground truth data from inside Neptune's atmosphere, rather than inferences made from distant observations. The gap between what we know about Neptune now and what an orbiter mission would reveal is difficult to overstate. It would be like the difference between studying Earth from the Moon with a telescope and actually landing here. Every major scientific question about Neptune, the source of its excess heat, the structure of its interior, the mechanism behind its storm cycles, the nature of Triton's potential ocean, could be directly addressed by such a mission. The decision of whether to send it comes down to a simple and uncomfortable truth. Neptune is extraordinary. It may be the key to understanding the most common type of planet in the galaxy, and we have been waiting for 35 years to go back. When scientists study Neptune, they are not just studying one distant blue world. They are studying a class of planet that appears to dominate the galaxy. The planets orbiting other stars fall into several categories based on size and mass. Rocky worlds like Earth are one category. Gas giants like Jupiter are another. And then there is the middle category, worlds larger than Earth but smaller than Jupiter, often called sub-Neptunes or ice giants. Surveys of exoplanets have found this middle category is extraordinarily common. It may be the single most abundant type of planet in the Milky Way. Somewhere between 30 and 50% of all star systems examined appear to contain at least one planet in this size range. And yet scientists understand them the least of any planetary type. The reason is simple. We have no examples of this type of planet within close enough range to study in detail. The closest example is Neptune, and Neptune has only been visited once, briefly, 35 years ago. Every time scientists try to interpret the atmosphere of a distant sub-Neptune exoplanet using telescope data, they rely on models that were built using Neptune as a baseline. If those models are wrong because the Neptune baseline is poorly constrained, the interpretation of the exoplanet data is unreliable. There is a specific and urgent example of why this matters. Telescopes like the James Webb Space Telescope are now capable of analyzing the atmospheres of exoplanets by studying which wavelengths of starlight get absorbed as they pass through a planet's atmosphere. Different molecules absorb different wavelengths. By comparing the light that passes through an exoplanet's atmosphere to the light that does not, scientists can identify what gases are present. This technique has already detected water vapor, carbon dioxide, and methane in the atmospheres of some exoplanets. Scientists are now looking for more complex molecules, including potential biosignatures, chemical compounds that could indicate biological processes. To interpret those signals correctly, scientists need accurate models of how planetary atmospheres work across a range of sizes and temperatures. Neptune sits at a critical point on that range. Getting Neptune right makes the models more accurate across the board. A Neptune orbiter mission would directly improve the scientific community's ability to analyze the atmospheres of potentially habitable exoplanets. The connection runs from a frozen blue world at the edge of our solar system to the search for life among the stars. That connection is direct, measurable, scientifically serious. And yet, the mission waits. Meanwhile, Neptune continues doing what it has always done, generating its mysterious heat, spinning its supersonic winds, growing and destroying storms, pulling Triton toward its eventual destruction. Completely indifferent to whether we are watching or not, Neptune's blue is famous. Every photograph of the planet shows that deep, vivid electric blue. It has become one of the defining images of the outer solar system. And you already know part of the reason. Methane in the atmosphere absorbs red light and reflects blue. But here is the problem with that explanation. Uranus has methane too. The two planets are often described as twins, similar in size, similar in composition, similar in distance from the inner solar system. Both are classified as ice giants. Both have methane in their atmospheres in roughly similar proportions. Uranus is pale blue-green. Neptune is deep, vivid blue. If methane alone explained the color, both planets should look the same. They do not. And that difference has puzzled scientists for decades. The leading idea today involves a compound scientists call the unknown absorber. Something in Neptune's atmosphere, something that Uranus either has in much smaller amounts or lacks entirely, is absorbing additional wavelengths of light and pushing Neptune's apparent color deeper into the blue range. What that compound is remains unknown. Scientists have proposed several candidates. One possibility involves chemical reactions driven by Neptune's internal heat. Because Neptune generates significantly more internal energy than Uranus, its atmosphere is more active, more thoroughly mixed, and subject to more intense convection. This greater mixing might produce a different chemical environment, generating compounds in Neptune's atmosphere that never form in Uranus's more sluggish air. Another possibility involves the ultraviolet light from the distant star reacting with the methane and other gases in ways that are slightly different between the two planets. These photochemical reactions can produce complex organic molecules that have different colors and different light-absorbing properties. The honest answer is that scientists do not know what the unknown absorber is. They have never directly sampled Neptune's atmosphere to find out. All they know is that something is there, changing the color, and that Uranus lacks it or has far less of it. This mystery is a perfect example of how little we understand about ice giant atmospheres. But the color mystery points to something even more important. The fact that two planets with nearly identical basic compositions can have such different appearances tells scientists that composition is not the only thing that matters. The dynamics of the atmosphere, the internal energy driving it, the mixing and chemistry happening inside it, all of these shape what a planet looks like from the outside. This means that when scientists look at a distant exoplanet and measure its color and spectrum, they cannot read composition alone. They have to understand the dynamics. They have to know how active the atmosphere is, how much internal energy is present, how mixed and chemically complex the gas is. Neptune versus Uranus is the clearest possible demonstration of that lesson, sitting right here in our own solar system. Two planets, similar ingredients, completely different results. And that difference traces back in part to the same mystery that runs through this entire story: Neptune's internal heat. Let's take a step back. You have now traveled through nearly the entire story of Neptune, from its violent atmosphere to its strange interior, from its captured moon to its fading rings, from its single brief visit to the missions waiting to return. And one theme runs through all of it: Neptune keeps breaking the rules. Planets this far from their star should be frozen and quiet. Neptune is screaming, cold planets should have slow, sluggish atmospheres. Neptune has the fastest winds in the solar system. A planet's internal heat from formation should be largely gone after 4.5 billion years. Neptune is still running hot. Moons form from the same material as their planet and orbit in the same direction. Triton arrived from somewhere else and orbits backwards. Rings should spread evenly around a planet. Neptune's rings are clumped into arcs. Storms the size of Earth should persist for centuries. Neptune's storms vanish in years. Every single major feature of Neptune violates what simple models predict. And this is not a failure of science. It is a triumph of observation. Scientists built the initial models with the information they had. Neptune is the data point that forces those models to improve. Every broken rule is a new constraint that pushes planetary science forward. This is how science actually works. A theory makes a prediction. Reality breaks the prediction. Scientists build a better theory. Repeat. Neptune has been breaking predictions and forcing better theories for decades. The diamond rain was proposed as a theory to explain the internal heat, tested in labs, and found to be plausible. The migrating planet model was built in part to explain Triton's backwards orbit and the structure of the Kuiper belt. The resonance mechanism for the ring arcs was developed because the arcs existed and should not have. Every mystery on Neptune has produced new physics, and there are still mysteries we have not solved. The excess heat that no model fully accounts for, the unknown atmospheric absorber that makes Neptune more blue than Uranus, the unexpected cooling of the stratosphere, the internal structure of the deep mantle, which has never been directly observed. These are not small gaps. They are fundamental questions about one of the most common types of planet in the galaxy. Neptune is not an edge case. It is the rule. The ice giants sitting at the dark edges of solar systems across the Milky Way are not exotic exceptions. They are among the most abundant worlds in existence. Understanding Neptune means understanding the dominant category of planet in our galaxy. And we built our entire picture of this extraordinary world from a few hours of data gathered by a spacecraft that launched when the internet did not exist. The next generation of scientists looking at Neptune will have better tools. The James Webb Space Telescope is already returning data that changes what we know about outer solar system chemistry. Future missions will go further. But right now, in this moment, Neptune is out there, running, screaming, defying. 3 billion miles away, winds are blowing at 1,300 miles per hour. Diamonds are falling through the interior. A doomed moon is spiraling closer. Storms are rising and dying in the blue clouds. And we are just beginning to understand what it means. Nobody has ever heard Neptune. Sound does not travel through space. There is no medium to carry it between planets. The screaming winds of Neptune exist in total silence from the perspective of any observer outside the atmosphere. But that does not mean Neptune is silent in every way. Voyager 2 carried an instrument called a plasma wave detector. As the spacecraft flew through Neptune's magnetosphere, this instrument picked up oscillations in the charged particles around the planet. These oscillations are electromagnetic waves, not sound waves, but they can be converted into audio frequencies that human ears can process. Scientists did exactly that with the data from Voyager 2. They translated the electromagnetic oscillations from Neptune's magnetosphere into sound. The result was strange and haunting, a shifting layered hiss with rising and falling tones, punctuated by sudden pulses, something between radio static and music. Scientists called it the plasma chorus of Neptune. These sounds are real. They are a direct translation of something Neptune is physically doing in its magnetosphere. The shifting tones reflect changes in the density and speed of charged particles as the tilted, wobbling magnetic field sweeps them into different configurations. Each pulse corresponds to a real event, a burst of charged particles, a shift in the magnetic field, an interaction between the solar wind and the magnetosphere. You can listen to Neptune without being there. The electromagnetic signature of its magnetospheric chaos has been recorded and made audible. And that record is a reminder of something easy to forget when talking about planetary science in terms of numbers and models and missions. Neptune is a real place. The winds there are real. The diamond rain is real. The storms are real. Triton's geysers are real. The backwards moon is slowly and irreversibly falling toward a gravitational death. And that is real. The planet is sitting out there right now, at this moment, doing everything described in this story, entirely indifferent to whether any human being ever goes back to look at it. It existed for 4.5 billion years before anyone on Earth knew it was there. It will exist for billions of years after any mission we could currently conceive of has ended. Science gives us language to describe it and models to understand it. But the thing itself, a world of screaming ice and diamond rain and magnetic chaos at the edge of the solar system, is beyond what language can fully hold. This distance, both the physical distance in miles and the conceptual distance between human experience and what Neptune actually is what makes planetary science so compelling. We are reaching across space with instruments and mathematics to understand things that no human has ever directly experienced and may never directly experience. And every time we find that Neptune breaks a rule, it reminds us that the universe is under no obligation to behave the way we expect. The most honest thing science can say about Neptune is this: we know more than we did, we know less than we need to, and the planet is more extraordinary than we imagined. Neptune holds a title. It is the last of the 8 recognized planets in our solar system, the outermost, the final entry on the list. Everything beyond it, the Kuiper belt, the scattered disk, the distant Oort cloud, falls into the category of smaller objects, dwarf planets, icy bodies, comets. Neptune is the edge, and that position matters scientifically in ways that go beyond symbolism. Neptune acts as a gravitational shepherd for the entire outer solar system. Its enormous mass, about 17 times Earth's, shapes the orbits of the countless small bodies in the Kuiper belt just beyond it. The structure of the Kuiper belt, where objects cluster and where they are sparse, directly reflects Neptune's gravitational influence over billions of years. Pluto's orbit, for example, is locked in a specific relationship with Neptune's. For every 2 times Neptune goes around the star, Pluto completes exactly 3 orbits. This is not a coincidence. It is a gravitational resonance that Neptune locked Pluto into long ago. Pluto will never collide with Neptune because the resonance ensures they are always far apart when their orbits come closest. Thousands of other objects in the Kuiper belt are similarly corralled by Neptune's gravity. They have been sorted into resonant and non-resonant populations, pushed and pulled over billions of years into the patterns we observe today. Neptune did not just migrate to its current position, it reorganized everything around it in the process. The outer solar system as we know it is Neptune's creation as much as anything else, and at the edge of that creation, Neptune sits and continues its work, slowly tightening its gravitational grip on Triton, slowly shaping the orbits of the Kuiper belt objects beyond, slowly radiating its mysterious excess heat into the cold darkness. Standing at the edge of the solar system's planetary roster, Neptune is the last thing you encounter before the darkness deepens. And it turns out the last thing is the most violent thing, the most mysterious thing, the thing that breaks the most rules and answers the fewest questions, that is poetically fitting and scientifically important. Because planets at the edges of solar systems, the outermost gas giants and ice giants, appear to play a crucial role in shaping the entire system around them. The position of Jupiter in our solar system, far enough out to deflect comets and asteroids that might otherwise hammer the inner planets, is considered one of the factors that made stable, complex life on Earth possible. Neptune's role at the outer edge may be equally fundamental in ways we do not yet fully understand. We built civilizations on Earth, developed science, built telescopes, and launched spacecraft, and at the end of the planetary list, we found a world that has humbled every model and exceeded every expectation. Neptune is the last planet, and it turns out the last planet is the one with the most left to teach us. Of all the mysteries in this story, one sits above the others. It is the question that ties everything together: the heat, the winds, the storms, the diamond rain, the captured moon, the ring arcs. All of these trace back to a single unresolved issue. Why does Neptune produce so much more energy than it receives? Every other major discovery about Neptune, every phenomenon described in this story, either flows from that excess heat or feeds back into the question of where it comes from. The supersonic winds are powered by it. The rapid storm cycle depends on it. The diamond rain contributes to it. The capture of Triton may have added to it. The cooling of the stratosphere may be connected to changes in how it escapes. Everything on Neptune is a consequence or a clue. And scientists do not have a complete answer. The leading candidates, residual formation heat, diamond rain friction, and tidal heating from Triton's capture, are each plausible. Each contributes something, but when scientists add up the estimated contribution from each one and compare it to the measured total heat output, there is still a gap. The numbers do not close. Something is missing. Either the estimates for the known sources are too low, or there is a source not yet identified. One idea that has gained traction in recent years involves a process called double diffusive convection. In a fluid, where two different properties are being transported at different rates, such as heat and salt in the ocean, convection can organize itself into layered structures that transport energy differently than simple mixing would. If Neptune's interior has this kind of layered convection, heat from the deep interior might be trapped more efficiently and released more slowly, sustaining a higher heat output over a longer period than simpler models predict. This is a promising idea. It does not require any unknown source. It just requires that the interior is more complex than early models assumed. And given everything we have learned about Neptune, a more complex interior than expected is entirely consistent with the pattern, but it has not been confirmed. Confirming it would require measurements of the interior that only a dedicated orbiter mission with a gravity science instrument could provide. The most fundamental question about Neptune cannot be answered from Earth. This is where the science stands. A planet 2.8 billion miles away, producing energy we cannot fully account for, powered by a mechanism we cannot fully observe, sitting at the edge of the solar system, waiting for a spacecraft that has not yet been built. The question is known. The tools to answer it exist. The mission is designed. The only thing missing is the decision to go. Pull back from Neptune for a moment. Come back to Earth. You are standing on a rocky surface, under a sky with the right amount of atmosphere to breathe and the right temperature to survive. Liquid water covers most of the surface. A magnetic field wraps around the whole planet, deflecting the charged particles from the star that would otherwise strip the atmosphere away over millions of years. A large moon, comparatively close, stabilizes the tilt of Earth's axis and moderates the seasons. Everything about Earth's ability to support life depends on a precise balance of factors, and scientists studying Neptune have learned things that deepen the understanding of just how fragile and specific that balance is. Neptune's magnetic field, for example, shows what happens when a magnetic field is generated in the middle layers of a planet rather than the core. The result is chaotic. The field is offset, tilted, unstable. It does not provide the kind of reliable shielding that Earth's field does. If Earth's magnetic field behaved like Neptune's, charged particles from the star would be dumped into the atmosphere at random locations across the planet's surface. The radiation environment would be far more intense and far less predictable. Earth's stable, core-generated magnetic field is one of the reasons the surface is habitable. Neptune shows us what a planet looks like when that stability is absent. Neptune's weather system shows what happens when multiple energy inputs operate simultaneously without a stable dominant source. The result is extreme, rapid, and unpredictable. Earth's weather is complex, but it has a dominant and relatively stable energy input from the star heating the surface. That dominance gives Earth's atmosphere a structure that allows life to operate within predictable enough conditions for organisms to evolve, adapt, and flourish. Neptune's atmosphere has no such stable structure. The multiple competing energy sources create a system that is too chaotic, too variable, too extreme to allow any biological chemistry to organize itself. The contrast between Earth and Neptune highlights exactly what biological life requires: stability, predictability, a dominant energy source, a protective magnetic field, a surface where temperature and pressure fall in the range where chemistry can operate at the pace biology needs. Neptune fails every one of these requirements. But understanding exactly how and why it fails each one makes the requirements themselves sharper and clearer. Scientists designing instruments to search for life on distant exoplanets use these requirements as filters. They look for planets where the magnetic field appears stable, where the energy input is dominated by the star rather than internal sources, where the atmospheric chemistry falls in the range associated with moderate temperatures and pressures. Neptune is the control case, the comparison point, the planet that shows you exactly what life does not need, and in doing so clarifies exactly what it does. The study of the most violent world in our solar system sharpens the search for the most peaceful one. You started this story looking at a painting, a smooth, perfect, deep blue sphere, distant, calm, beautiful. You know now what that beauty hides. Winds blasting at 1,300 miles per hour across a planet 57 times the volume of Earth. Storms the size of our entire world erupting from convection currents driven by heat from an interior that has been running for 4.5 billion years. Diamond rain falling through a crushing mantle of hot, electrically charged fluid. A magnetic field generated in the wrong place, pointing in the wrong direction, lurching through space and dumping energy into the atmosphere at unpredictable angles. A moon captured from the outer solar system, flying backwards in a death spiral that will end in the most spectacular ring system our solar system has ever produced. Geysers on that moon erupting in a world so cold that nitrogen freezes solid on the surface. A ring system already in place, made of the rubble of ancient moons destroyed in Neptune's violent youth, fading slowly as its particles drift and disperse. A stratosphere cooling for reasons scientists cannot yet explain. An internal heat surplus that no model has fully accounted for. An unknown compound in the atmosphere changing the planet's color in ways that hint at chemistry we have never directly sampled. A gravitational influence stretching through the Kuiper belt and shaping the orbits of thousands of smaller bodies, including one small world locked in a permanent gravitational relationship where it completes 3 orbits for every 2 of Neptune's. All of this from one brief flyby, 35 years ago. Neptune is not a closed book. It is a book where scientists have read the first few pages and found that every sentence raises 10 new questions. The more we learn, the more extraordinary the planet becomes. The more extraordinary the planet becomes, the more urgent the case for going back. And this matters beyond curiosity. Ice giant planets appear to be among the most common worlds in the galaxy. Understanding Neptune is understanding the dominant planetary type in the Milky Way. Every mission that returns to Neptune, every instrument that measures its interior, every probe that descends into its atmosphere, makes humanity better at reading the universe around us. We look up at the night sky and wonder whether other worlds exist that could support life. Answering that question requires building accurate models of how planets work. Neptune is a critical piece of that modeling. Getting Neptune right improves our ability to read every other planet we find. 3 billion miles from Earth, under a sky darker than any night you have ever experienced, a blue planet is roaring. Its winds have never stopped since the planet formed. Its storms rise and fall in years. Its moon is falling. Its interior is burning with heat that has no complete explanation. And we are only beginning to understand it. The most violent world in our solar system is also one of the most important. It sits at the edge of the planetary list, past the last familiar milestone, in the dark where the solar system fades into interstellar space. It has been out there for 4.5 billion years. It will be out there long after any record of today survives. And it is waiting.